Hello, my name is David Villegas Prados, and I'm going to present the progress that I've been doing in the indirect characterization of electrospheric thruster. I think Borja before commented that he was working more on the direct part of, of the characterization and working more on the indirect part. So the motivation, similar as my colleague in United Space, we're trying to develop the next generation of electrospray propulsion. Some of the characteristics of this system, which makes them really attractive, is that they have really high efficiency, even at low power. They have a high thrust to power ratio, similar to Hall effect thruster. It's high compact. We can fit a system like this in a CubeSat, or even if it goes into really small platform like nanosatellites. It has low thermal loads, and we can select the total impulse and the thrust. So just a brief introduction on electrospray for those that are not that familiar. This is a cone of the electrospray thruster, and a emitter is composed of many of these cones, which compose, and then a thruster can have many of these emitter. In here, in this image, we have two different parts. We have the emitter and the extractor, and then the liquid that is stored in a reservoir. By applying an electric field to the liquid between the extractor grid and the emitter, the liquid creeps through the emitter thanks to this nanotexturization, and it reaches the top. And when the electric field is strong enough, we are able to extract particles from this liquid, and thanks to the same electric field, with respect to the extractor, we are able to accelerate and produce the thrust. Now, the key of electrospray propulsion is on the propellant, which are the ionic liquids. These are a stable liquid in vacuum. They are composed of positive and negative particles. So if we apply a positive potential, we are able to extract positive particles, and if we apply a negative potential, we are able to extract negative particles. This is useful because we are able to self-neutralize the plume without the need of a cathode. They are stable in vacuum, and they have negligible vapor pressure, which is good for their storage. They are really easy to handle. You can use them in the lab with just some gloves and goggles. You don't need nothing else. We're able to achieve both the extraction and the acceleration with the same electric field, and so we don't have losses related to magnetic fields, like for example in plasma thrusters. And important characteristic now is that the accessibility is quite easy. There are a few providers here in Europe, so we don't need the need of external suppliers from China, for example, which now could be an issue. So the goals of my PhD are first to build a suite of diagnostics to be able to test and characterize indirectly the electrospray thruster. This includes a retarding potential analyzer, a Faraday cap, the time of flight mass spectrometry, which includes also the high voltage pool generator that drives the gate, and the computed tomography. Thanks to this suite of diagnostics, we've been able to analyze the thruster variables and how they affect the propulsive performance. This is the voltage influence and temperature dependence. These are variables that we can actively control. So, and this information, I think I presented here 2 years ago in the doctoral meetings, and resulted in a paper that was published last year related to this impact of the propellant temperature and the voltage. And I have been able also to test different propellants, a total of 7 different ionic liquids, which this information was also presented last year in these doctoral meetings, and just a couple months back it was published, both of them in Acta Astronautica. So I'm gonna focus now, which this last year I've been more focused on the development of a new high voltage pool generator. So the one we developed was a simple one that we got from some book that we are able to put together, but having a reliable and a controllable high voltage pool generator is something that is really useful when you're doing this test. So I was focusing on improving this diagnostic and the computed tomography. So first of all, I think I cannot talk about the high voltage pool generator and what I've been doing without talking about the time of flight, because the time of flight is the key diagnostic of my PhD. Everything, all the results that I get, everything that I do is related to this. So going back to the question that you had before, so how it works, basically, we have the thruster, and at the end of it doesn't have to be a tube, it's just at some distance that we call the flight length, we have a collector with a repeller in front. avoid the collection of secondary species. And in the middle, we have a deflection gate. Now, the deflection gate can have many different types. In our case, we use the deflection gate because it's relatively easy and simple to manufacture and to implement. And the high voltage pull generator drives this gate with a differential potential of plus minus some voltage. And when we apply this potential, all the particles that are going into the collector will be deflected to an angle. Now the angle and the potential is size, so the particles are not able to collect at the end of the flight length, and only the particles that have passed already the gate are able to reach the collectors, because the electron spread thruster can emit different types of particles, different masses, different charges. They're going to have different velocities, so at the end we get a distribution of particles, and we're able to estimate what is the population. From this time of flight technique, we're able to estimate thrust, ISP, and efficiency. So at the end, it's like a diagnostic that gives you a little bit of everything. Now, going forward to the high voltage pull generator that I've been developing in the past year, some key characteristic of this is that we have miniaturized the DC-DC, and we have put everything into the PCB with a planar transformer. That means that all the parasitic currents, all the components that are also SMD, they go through the PCB. This reduces a lot the times that go between the components, which will be useful at the end for the rise and fall times. We are able to control the voltage that we want, the frequency, and the duty cycle. So that is useful, because depending on the length on your flight length, or on the liquids that you're using, the distribution you have, like maybe you want to have more or worse resolution. So with this high voltage pull generator, we're able to adjust to our needs. And also we have included a low voltage output monitor. So usually what we were doing, we were getting the monitor from the control signal that we give to the pull generator. We have a low voltage signal that then we amplify to the high voltage, but of course there is a delay between the creation of this low voltage signal to the high voltage signal. So we create a low voltage output monitor, which is just the same high voltage signal that is just translated into low voltage again. Now this is the results of the high voltage pull generator. This is directly the raw data from the oscilloscopes, and the important thing here is that we're able to reduce the rise time. In the first version that we had, the rise time was 220 nanoseconds, which is enough for some of the applications that we are doing and for the flight length that we have. But of course, if we're moving to, for example, a shorter facility, or we have a liquid with a lot of fragmentation that have different populations that close together, then having this higher rise and fall times will be useful to differentiate them. And we are able to obtain less than 30 nanoseconds for both the rise time and fall times for all the voltage. Now, moving to the computed tomography, which is the other diagnostics that I've been working this past year. Now, the computed tomography is the 2D spatial reconstruction of the emission map of the emitter. So the emitter is composed of many of these cones, but of course, when we are operating, it doesn't mean that all of the cones are emitting the same. And the plume is not actually symmetric. Actually, it's quite asymmetric in a sense that maybe from your emitter, like maybe 50% of the emitters are actually working, or 70. Like you don't really know, because at the end you get one value, you're emitting this current, but maybe this current is not emitting uniformly through all the cones. So the idea behind the computed tomography is to characterize these emission sites, and this is really useful to trace it back to the manufacturing process. Ideally, if the emitter is perfectly manufactured, all the cones are the same, and all the detectorization is the same, you should achieve the same emission per cone. But in reality, this is not the case. This diagnostic allows you to know exactly where in your manufacturing process which cones are not being manufactured properly. So these are some simulations. Before I constructed the tomography, I ran some simulations to see more or less how it would look like. I forgot to mention that we have a wire that we pass through the emitter, and we have different swipes in the radial and the angular direction, and we get line integral at different positions. If we combine them and then we do the random transform, we are able to obtain something like this, basically. So this is a simulation of the emitter at a distance, if we pass the wire at a distance 1 millimeter from the extractor, okay? And this would be like the ideal, how you would see it if the emitter would actually emit light, how you would see it, because in reality, electrospray, they don't emit light, like you don't see anything. And this is the reconstructed map if we would do the tomography with 100 points in the radial direction and 30 points in the angular direction, which we observe is quite good. And this is the goal, that with this diagnostic we're able to know exactly which of the cones are actually emitting. This is the setup. So I don't have data of this because this is a picture of yesterday actually. So this is something that will be, the data of this hopefully will be presented in IPC in Toulouse next month. So at the moment we are testing this setup, but here we can observe this is a linear stage that moves in this direction, and then the thruster is mounted on a rotary stage that rotates. And here you probably won't see it because the wire is 25 microns of width. So there is a wire here, so the linear stage sweeps in this direction, and then the rotation stage is rotating, and then we get all these measurements at different positions. Then by doing the post-processing, we are able to reconstruct this map. And I would like also to talk about some of the results that I already mentioned, but I think they are more or less the highlight of the PhD. And since this is probably the last doctoral meeting that I'm doing, I would like to present them. This is the first data that I obtained, which is like the voltage and temperature dependence. We found that in the spray thruster.
David, you can do that, but you need to go fast. You have already
this one slide.
Okay.
Yeah. So the important characteristic here is that we found that with temperature we obtain more thrust because we have more current and more droplets which have higher mass, so they contribute more to the thrust at the expense that we are losing ISP, of course, because of these heavy particles and the efficiency. And the other information regarding the iron liquid studies, we found that even though it is the most common liquid, the MEBF4 still is the best in terms of efficiency and thrust to power ratio. And it has some problems, the MEBF4, like the sterility, because it absorbs a lot of water, and the fluor is not a good friend of the silicon that we use for manufacturing the emitters. But we found that some of the key characteristics that we would like for our thruster, which would be a high viscosity and high conductivity. And so some of the conclusions: the time of flight is the key indirect diagnostic that we use to characterize the electrospray thruster. We found that increasing the voltage yields higher current, higher thrust, and also increasing the specific impulse and efficiency at the expense of power, and also the limitation that our system have of how much voltage we can deliver. And increasing the temperature yields higher current and thrust, but lower specific impulse and efficiency because of the creation of these heavy droplets. We also found that MEBF4 presents the higher performance among all liquid tested, but there are a bunch of iron liquids and they can be synthesized, so it's just a matter of finding the one that fits all your needs, or even maybe you're able to produce it. And finally, the tomography will give us more insight on the individual emission sites of the thruster emitters and how we can trace it back to the manufacturing process. And then some of the conference, well, the new ones that I have been in the past year was UCAS last year in summer, and then the junior articles. Last year we were able to publish the one related to the impact of the propellant temperature on the externally wetted electrospray thruster. Just 2 months back we published another one in ACTA related to the study of this ionic liquid, and last month it was submitted a third paper regarding the construction of this high voltage boost generator that I was talking before. We submitted to the research of scientific measurements, and the future work for me would be just to write and defend the thesis. Thank you.